Okay, next up will be Deelan. She'll speak to you about integer invariants of Abelian Cayley graphs. We were real happy to have some support suddenly to do research this summer. Deelan's been great to work with. We had a lot of fun, worked really hard. Actually, Deelan spent most of her time in a small office working with MENA students, these two guys back here, Justin and Brock. So yeah. I think maybe you add one more student in that office might be a good experience to taste of grad school. Okay, so I'll let Deelan take it away now.
So I work with Dr. Ducey, and we study the integer invariants of Abelian Cayley graphs. And what we're going to define a graph to be is simply vertices that are connected by edges. So if you take that definition, a graph can get pretty ugly. However, when we limit ourselves to the Abelian Cayley graphs, what we deal with are very nice and organized and symmetric. So the simplest example of an Abelian Cayley graph is this cube. So you see that it has the vertices labeled as follows, and what we're going to do is encode the physical properties of this cube into the mathematical structure we call a matrix. And in doing so, we're able to compute different numeric and algebraic properties of the matrix that will in turn tell us more about the graph itself. So the way that we do this is we have our matrix, and we're going to index the rows and the columns by our different vertices. So say you're interested in that the 0, 0, 0 and the 0, 0, 1 position. You see that between these 2 points, there is an edge connecting them, so we denote that relationship with the number 1. And so if you take the 0, 0, 0 and the 1, 1, 1 entry, there is no edge directly connecting those 2 points, so we have a 0 right here. So you continue this process over and over again until you fill out your matrix, and it would look like this. And what this is called is an adjacency matrix, because it tells you when 2 edges are adjacent. You might also hear me refer to it as an incidence matrix, because all an incidence matrix is just it defines when 2 things are related. Okay, so there's a lot of zeros and ones everywhere. So this right here is just a pictorial representation of that same matrix. A black denotes the entry 1, a white denotes the entry 0, and this square up top, that's 1 pixel, so that's 1, 0 entry. And the border is just something I added to make it look prettier, it doesn't mean anything. And so what we're going to do is perform different row and column operations to transform this into a diagonal matrix. And this diagonal matrix is in what's called its Smith normal form, because if you go down the diagonal, you see those numbers divide each other. So 1 divides 1 all the way down, and then we get to 1 divides 3, and then 3 divides 3. So every integer matrix has a Smith normal form. And one use of Smith normal form is, say you take the set of all n by n matrices, integer matrices, and so we say this is all of them. So in here you'll have different incidence matrices, you'll have just integer matrices, and you'll have some that are in Smith normal form. So if we partition this up into different classes, it turns out that each of these classes will have only one Smith normal form. So if you want to know if 2 graphs are isomorphic, you find their incidence matrices, and then it'll turn out that their incidence matrices will have the same Smith normal form, so they'll be in the same class. So that's one application of this. And so this is just a more formal definition of what I just said. So every integer matrix has a Smith normal form, and you see a divisibility condition right there. And so just a review of those row and column operations that we're allowed to perform are we can swap any 2 rows and columns, we can multiply any row or column by a non-zero integer, and then we can add an integer multiple of 1 row or column to another. So let's go back to our incidence matrix. This is the way we formed the incidence matrix for the cube. However, this isn't the only way you can do it. The matrix will look different, but it will pretty much have the same exact information. So the first thing we're going to do is negate all of our entries. And then next, going across the diagonal, you see we have all zeros, but instead of putting zeros, what we're going to put is the degree of each vertex, and the degree is simply how many edges are coming out from it. So we're going to have 3's going across the diagonal. Now this, like the last matrix we formed with the 1s and 0s, those are called adjacency matrices. And this matrix is called the Laplacian matrix. And again, some magic happens, and we put it into its Smith normal form. And because those numbers across the diagonal, again, divide each other, we have 1 divides 1, and 1 divides 2, 2 divides 8, and 8 divides 24. And an application of this is if you take the product of those diagonal entries, ignoring that last zero, what you get is the number of spanning trees the cube has. And so a spanning tree is you take your cube, and what we're going to do is create a path that is connected and that hits every vertex. However, we can't have any cycles in it. So just one example of a spanning tree would be this. So we start here, like go up, over, down. So you see that we have hit every vertex, but we have not created any cycles and we remain connected. So this tells us that the number of spanning trees this cube has is the product of those numbers, which is surprisingly 384. So just going back to the definition of Smith normal form, we're going to learn a little bit of terminology really quick. So invariant factor are those numbers across the diagonal. And then if we factorize those numbers, we get what's called elementary divisors. So just a quick example. Say we had a matrix and this was its Smith normal form. You can just read off the invariant factors. They would be 1, 3, 6, and 60. However, when we factorize those numbers, we get as the elementary divisors, we have 2, 2 squared, and then we have 3, 3, 3, and 5. So if I say the multiplicity of an elementary divisor, that's what I mean. I'll say like 3 occurs 3 times. So going back to the title, integer. Everything that we work with will be an integer. We won't have any fractions or any irrational numbers. And the next one is invariant. Invariant is a property that doesn't change. So Smith normal form is one kind of invariant. So regardless of the way you order your rows and your columns, so if you shuffle them all up, you would still end up the same with the same Smith normal form. And then finally, an Abelian Cayley graph. If you remember at the beginning, I defined a graph just to be a bunch of edges and vertices. However, if our vertices come from an Abelian group, a finite Abelian group, we have the Abelian Cayley graph. So two things make up our Abelian Cayley graph: the Abelian group and our connecting set. So what is a group? A group is simply a set of elements with an operation. So thinking back to our cube, the set of elements we had were those vertices, and the operation we're under is addition mod 2. And then in order for it to be a group, it also must meet these 4 conditions. And the one I'm going to point out is that the identity is the 0, 0, 0, because we're going to need it in just a second. And so the second necessary condition is we need our connecting set. So our connecting set tells us when there is an edge between 2 different vertices. And we're going to define the set to be the set of vertices such that all the tuples where you have exactly one component that is not the identity. So in the cube case, it would be these 3 vertices because only one of those are not the identity, which is 0. And so an edge exists between 2 points if the difference between them lands in E, and remember the difference we're doing under mod 2 as well. So the goals of this research were to predict the different elementary divisors and their multiplicities for various incidence matrices, and we also wanted to recover the results of others in the field by using a different technique. Their main focus was row and column operations, but we ended up using character tables. So in our pursuit of these elementary divisors, we found out that the spectrum of a matrix provided us with vital information. And the spectrum of a matrix is simply a list of eigenvalues and its multiplicity. And if you forgot what an eigenvalue is, so an eigenvalue, lambda, of a matrix is a non-zero vector such that if you hit your matrix with that vector, which you pop out, is a scalar multiple of that vector. And so at the most general level, there is no connection between Smith normal form and eigenvalues. We'll see with this example. So you see with this first one, it's a diagonal matrix, so we can just read off the eigenvalues because the eigenvalues of a diagonal matrix are just the entries themselves. And then the same thing with the upper triangular matrix. The eigenvalues will just be those diagonal entries. So you see that these 2 matrices have the same eigenvalues. However, the first one is already in Smith normal form because that divisibility condition is met. So the values for that will again be 2, 2, and 2. However, when we perform our row and column operations, the Smith normal form will have the values 1, 1, and So at the most general level, we said there is no connection between Smith normal form and eigenvalues. However, when we limit ourselves to the abelian groups, a connection does exist, and it's given by this theorem. So it says for primes not dividing the order of G, and the order of G simply means the number of group elements you had. So thinking back to the cube, we had 8 elements. So the multiplicity of a prime occurring as an elementary divisor, and then the elementary divisor would, when we broke up those factors into their primes, is the same as the number of eigenvalues, exactly divisible by that prime P we're interested in. So we see that eigenvalues are very, very important to us. And there is a known method to find eigenvalues, and this is given by this theorem. So what this does is you take your adjacency matrix and you hit it with the character table of the group. And what it pops out is a diagonal matrix, and your eigenvalues will be expressed as character sums. So what we're going to do is take these two theorems, combine them, and use them for different Abelian Cayley graphs. So the first one we're going to look at is called the Hamming association scheme. And with this scheme is you let G be your, you take the set of all tuples of length n with coordinates taken from an alphabet of size q. That means you have your length n vector, and you have cube choices for every position. And then we're going to define the relationship to be, so two things are related if they differ in exactly k coordinate positions. So this is an Abelian Cayley graph because we have our group, which is EQ cross EQ n times, and then we have our connecting set EK. However, this time EK is the set of tuples with exactly k components that are not the identity. And so just some examples of what this distance k mean is, so the Hamming distance between apple and smile is 3 because they differ in the first 3 positions. The distance between math and pool is 4 because they differ in every position. And then the distance between those 2 points is 2 because they differ in the first and last position. So if you pick your parameters n, q, and k, we can again construct that incidence matrix that we had earlier and find the Smith normal form of that. So what we found is that we can predict the elementary divisors for these matrices for primes that don't divide the order of our group. This is similar to the previous theorem that we just had, except we were able to extend the argument for cases when k was not 1, so up until k is n. The second one that we're going to look at is called the NQ graph, and this is just a specific case of the Hamming association scheme. And it comes from fixing your Q to be 2 and your K to be 1. So for every, there's 2 choices for every entry, and they're related if their distance 1 away. So, and then the n you decide to pick is the dimension you're working in. So when we picked 3, we were working in the three-dimensional cube. And you see that in fact every entry is either 0 or 1. And there is an edge connecting them when they are only distance 1 away from each other. So again, to see that this is an Abelian Cayley graph, we have our group, which is Z2 cross Z2 n times, and then we have our connecting set E1, which is again the set of tuples that have exactly 1 coordinate that is not the identity. So when we worked with this n cube, we were trying to predict the elementary divisors, and it happens that when n is odd, we completely solve the case. However, when n is even, we run into some trouble. So we're just going to do an example of each. When n is odd, so when n is odd, we pick n to be 3. The order of our group is 8. So we have 8 elements. And then if you remember that long character sums formula we had for the eigenvalues, it collapses down to this, which gives us these eigenvalues and their respective multiplicities. So the first thing is, what don't we know? The theorem, Sim's theorem said that since 2 divides 8, we won't know anything about 2 occurring. However, 2 does not show up as an eigenvalue, so that's not going to cause a problem for us. And then it also says that since 3 does not divide 8, we can predict how many times it'll show up as an elementary divisor. All you have to do is count how many of those eigenvalues are exactly divisible by 3, which is 2 in this case. So knowing all that, and then also we're not considering 1 as a prime, so those end up taking care of themselves after you do know about the other primes. So this is the Smith normal form we get. And then whenever n is odd, this is what happens because all of the eigenvalues will be odd, and you won't have 0 showing up. So when you take the product of your eigenvalues, which is equal to the product of your elementary divisor, they both have to be odd. And you know there won't be any factors of 2 showing up, so you never run into any problems. So the second case is when n is even, and we picked 6. and when n is 6, the order of our group is 64. So then again, we have that same eigenvalues formula, and we're going to plug n in for that, and these are the eigenvalues we get with their respective multiplicities. And so, again, we're not going to know about 2, anything about the prime 2, and that's going to cause some problems soon. But what we do know about is 3, which comes from factorizing this. So if we want to know how many times 3 shows up as an elementary divisor, we count how many times it exactly divides those eigenvalues. And we see that 3 occurs twice from these 2 sixths. And then 0 we're not going to deal with again because it ends up coming from the rank of a matrix. And so it'll take care of itself once you deal with the other numbers. And so here's what the answer is. We have 2 showing up 12 times. So we asked ourselves, where does this 12 come from? We looked at a lot of examples, and do you guys have any guesses where it comes from? No? Okay. Yeah, so the 2, it ends up, we came up with this conjecture which states that the multiplicity of 2 to some power as an elementary divisor from this list is exactly equal to the number of eigenvalues that are exactly divisible by 2 to 1 power above that. So we're interested in the prime 2 to the first power as an elementary divisor. What we're going to do is go back to our eigenvalues and see how many of those eigenvalues are exactly divisible by 1 power above that, so 2 squared. And then this is where the 2 squared comes from. So 2 squared exactly divides -4 and 4, and these occur both 6 times, so we know that 2 will occur 12 times. And we haven't proved this, but we strongly, strongly believe it's true. So we're just going to generalize everything we did. You can pick any group you want, you can pick any connecting set, and then what we did not only applies for the adjacency matrix, but also for these matrices as well, the Laplacian, the timeless Laplacian, and the Seidel matrices. And we were able to recover the results of these 2 papers, except we used those character sums where they were more geared towards the row and column operations. So I'd like to thank my mentor, Dr. Ducey, for putting up with me these 8 weeks. Dr. O for coming in with a smiling face every single morning. Justin and Brock for breaking my computer and then fixing it. And then the JMU Department of Math and Stats for their support of me. Any questions? Yeah.
That's a really lovely piece of work, and I love that conjecture, but when you said you would really believe it's true, so I'm guessing you did a whole bunch of numerical experiments?
Yeah.
How far did you go? Roughly.
Roughly, I think we did up until n equals 10. So up until the 10 cube, we saw that this held. It was just a recurring pattern. When n was odd, we could get it. When n was even, it would not. But then those primes would match up if you go one.
Excellent. Right.
So at the end, you mentioned how you were able to get the known results from those 2 separate papers. Is it just like a different way of getting those results, or is your proof like so much shorter or slightly longer, or what's the significance?
It's their row and column operations. When you look at it, it's kind of confusing to see what's going on. So sometimes it would take like 2 to 3 pages for their proof to be finished. Whereas we used the character sums formula, and we got it in about a paragraph to see what the eigenvalues were.
Thanks again. Stop in about 5 minutes.